Alright, so finally we're just going to solve for dy dx, and we would get that 2y dy dx is equal to negative 2x. Divide both sides by 2y. We get dy dx is negative 2x over 2y. Cancel the 2's. And dy dx is equal to negative x over y. And so the key to, I think you'll note that this is a much simpler process than first solving for y, which we had to do on the left side, and then finding the derivative of something that's often going to be much more complicated and awkward, involving square roots and etc. So, and then lots of substitution in the end. It was a much more complicated process to find the derivative using the strategies that we have already learned. But if you can grasp this change of viewing y as a function of x, kind of like the chain rule, and what I have in purple down at the bottom there. So if we were viewing y as this function of x, so you would have x squared plus f of x quantity squared, then when you're trying to find the derivative of that, you would use the chain rule when you got to the f of x squared part. And the derivative of f of x quantity squared would be 2 times f of x times f prime of x. So, and the other thing that we're doing a little different here is that we're actually working with equations as opposed to just working with expressions. And so there's an equal sign, and what we're going to do is to take the derivative of both sides. So we're going to find two derivatives, and these two derivatives are going to help us find our dy dx. And in this case, the derivative of 1 was 0. So this is another way of looking at it, viewing y as a function of x. And since y is a function of x, when we find the derivative of something involving a y, we take the derivative of the outside, whatever it is, and then we multiply that times the derivative of y with respect to x, which is just dy dx, assuming we don't know what the function is that y represents. So in this particular case, I can rewrite the f of x again as y, and the f prime of x as dy dx, and then we're right back to where we had gotten above. So the key to doing implicit differentiation is to view y as a function. You don't see what that function is, but it is some function, and if it were y squared, finding the derivative of that, we're going to take the derivative of the outside, which is a square function, so we bring down the 2, multiplied by y, then we multiply that by the derivative of y, which is just the derivative of y is dy dx. And so that's kind of what, this is what we're doing in this particular section here. So I will show a few more examples of how this works, and there are a few twists and turns, caveats to working with implicit differentiation, but this is the first big idea.